Good morning. So welcome to lecture 26. So let's not spend too much time about this morning on your grades, but I did send you a rough projection of your grades. One common question, and probably I'm going to repeat this maybe 20 more times. If you're happy with your grades, you don't have to take exam 4 and final exam. Okay? Clear? And okay. So I sent an iClicker question about, yeah, good, thank you, about total internal reflection. And maybe we can take a step back. Basically, refraction occurs when light travels from one medium to another medium. And that medium can be the incoming medium or the first medium. The index that we use here is 1, can be more dense or less dense. And then the formula that we use is Snell's law. Not surprisingly, it is formulated by Mr. Snell. Maybe you're not familiar with the culture in science. When you formulate something important, you don't name it. You don't name that formula after yourself. You hope that your friends would name the formula after you. It's not a good taste to invent something significant and name it after you. Okay. Fermat also came up with a similar formula. And then when all lights get, well, an angle that gives 0 refraction, we call that critical angle. And that can only occur when, okay, let me show the results. Okay, so most of you answered A. So A basically says like from more dense to less dense, right? Which is the correct answer. The reason why it takes me a while because I need to do some math here. So if more dense to less dense, then in order for theta 2 equal to 90 degrees, which is the case for total internal reflection, then and the critical angle, theta 1 becomes critical angle, is equal to n2 divided by n1. And this number can only be real when n2 is less than n1. So, or n1 is larger than n2. So most of you got it right. Any question? Okay, good. So next is, last time I briefly talked about how we see lights. There are different steps, but actually, like anything in science, especially in optics, because optics is a very old subfield of physics, people came up with many theories. So the first one that I often read is Aristotle. So I think he said that the presence of objects will dictate how we see them. So there is no light. Basically, the presence alone is enough for our eyes to see it. And how to disprove that? You can put the object and the person in a dark room, and the person cannot see it. That's one. And then if you're a big fan of math, there is this guy, his name is Euclid, Ptolemy, Ptolemy. They say that actually every object emits some kind of rays. And that's how our eyes perceive seeing things, how our eyes see things. And how to disprove that? How if you want to disprove Euclid, how do you do that? Same thing. You put both in a dark room, and then if you cannot see the object, that means it's not a good theory. The first guy, again, I'm a big fan of this guy. His name, the first guy that get credited on the theory of ray light is Ibn al-Haytham. So my son's name is Haytham. He's sitting right there. And then this is one nice picture, Al-Hazen. So the Greek and Western world call Ibn al-Haytham Al-Hazen. It's a long story. Basically, he was born in Basra, like modern day Iraq. And then there are many interesting stories that you should read them yourself. But basically, he was not in a good term with the caliph or the king, and he was sent to house arrest or home confinement. And instead of getting depressed, he actually wrote a lot of books. I think there are 7 books of optics that is influential. He is many people credit him as the father of optics. Okay, he's the one who figured out that light actually travels along a straight path, which is something very obvious for us, especially for all of you, since you know Fermat's principle of least time. He also developed one way he proved that is by making a box with a pinhole, with a small hole, and he calls that camera obscura. So, and then that's the reason why in your smartphone there is a camera app. We use the word camera in honor of Haytham, Ibn al-Haytham. Okay, so basically, throughout this, for the rest of the class, we see objects. Part of it is hardware or wetware, but most of them is software in our brain. So our brain does computation. That's the point of this long slide. Okay. So any questions so far? So we're going kind of fast here. Next is because we process image, our brain actually process image if the software is not right, meaning every software has limitation, right? Canvas doesn't sync well with iClicker, for example. Your brain doesn't know the history of light. And because of that, we see illusions or mirages. And I think this discussion is a little bit longer than it should, than your perusal. So there are 2 types of mirages. One is when the object appears taller or at higher elevation, higher coordinates than the real objects. So this one is not Photoshop image, and this is a ship. This is not a flying ship, but your eyes and even camera see the ship above the ocean level. Okay. And then second, what we are familiar with is what people call inferior image, which is you can see the image of the sun or the truck or cars in front of you on the surface of the road in a hot summer day. But I want to go through this a little bit more detail. I think it's good because some of you have taken optics in your high school. Right? So, but for these 2 mirages, there are 2 YouTube videos that I recommend. So you should click and see and watch the videos. One is, so the first one is, we call it superior mirage. The name is not important in this class. You don't have to memorize whether it's superior or inferior. So one example is this flying boat, or in some folklores, people call it like ghost ships. So basically, in a summer day, in daylight, of course, because you need light to see objects in nature, and this is ocean. Okay, so that's one thing. Next is during daylight, there is temperature gradient. So actually, near the ocean surface, the temperature is lower than high above. High, so this is, I don't know, let's call this Y or Z, high temperature, okay? So that's one thing. And then next, next I switch the axis. The X is temperature, not Y, and Y-axis right now is refractive index. It turns out that in many material, well, when light travels in a medium with refractive index n, the speed slows down by n. Part of it depends on the density of the material. The higher temperature, the density decrease. Right? So I don't. Someday you will see this kind of plot with two y-axes. So the density decreases as the temperature increases. So rho, density decreases as the temperature increases. Because the density decreases, the refractive index also increases. And this is not the exact curve. Okay? So basically this one is low T. That means it's low temperature is low density, and low temperature is higher density. Sorry. Red is density and low refractive index, right? Similarly, here is low density and high refractive index. Because there is a change of refractive index, if this is the boat, I have to draw a boat. When it, and then the boat is actually big. So let's say to make the boats big, I'm just gonna do this. Okay. It goes to several layers. There is infinite number of layers here, but let's just assume there are 3 layers. Okay. Because the bottom one is let me take a, okay, so there is something not quite right here. Higher temperature is, all right, so basically, just, I need to check about this. But basically there is a change of refractive index. And let's say there are only 3 layers. So there is the light bends between layer 1 and layer 2. And then it bends again in layer 3. And then let's say this is the observers. Let's say this is you on a beach. What your brain sees, your brain interprets this angle here. So the boat is on an ocean surface, but your eyes actually see the boat above the ocean surface. Okay. I apologize for the, I need to check about the refractive index. But basically the idea is your brain doesn't know that there are different layers of medium, and your brain only interprets the angle, and because of that, it forms an image that is far, not far, but it's above the surface, like this. Okay. Good. So that's superior image. Basically, it looks like this. Should be high N, should be low N. Okay, good. This is high N. I don't know how so this is correct. High temperature. Yeah, so my plot was reversed. Okay. So the light travels from a layer with low refractive index to layer with high refractive index. The question is, can we have total internal reflection? Yes or no? I'm gonna send it to, can we have total internal reflection here? So A, yes. and B, no. Okay, let's spend 30 seconds. Low refractive index to higher refractive index. Right? Good. So light travels from low refractive index to higher refractive index. Can we have total internal reflection? I mean, the answer is right there, right? So 10 more seconds. 5 seconds, 3, 2, 1. Okay, so basically all of you got it right. So if you see, that's one way to do that is using your knowledge of Snell's law and total internal reflection. Another way is using this slide here. There is no total internal reflection on the superior mirage panel. But there are also cases in nature, especially in desert, like in Tempe, that the area that is closer to the surface is actually more hotter. For example, on Tempe, the area or the volume or the layer near asphalt road is hotter than, let's say, 10 meters above, or even 1 meter above. So in this case, the light get bent more and more. So let's say there is a car here, I don't know, Cybertruck, I don't know how to draw it, something like this maybe. It goes like this, and then there is another layer, let's say it even bends even more, and bends even more. And at some point, it will reach critical angle, which is here. And then there is no refraction. The light bounce. All of them are get reflected. And then, okay. And then let's say this is you. And then what you see, instead of seeing Cybertruck here, what you see is that you see Cybertruck here. Because your eyes, let me just extrapolate the angle. Your eyes doesn't know that there are many, many layers with different refractive index. So this is why we see mirage in summer in Arizona. Okay. It may show up on, no, sorry. Any questions? And then next, it turns out that life is complex. I know being pre-med is complex, but life is also complex. Turns out that refractive index also depends on wavelength. Anyone knows why? Why refractive index of a material depends on the color of light, the wavelength? Sarah. There are 3 Sarah, actually, not you. The other 2 never admit. The other Sarah. Are you Sarah? No, okay. Mabel. Well, I mean, what is the most important thing? Okay, important is subjective, right? But in this class, the most important concept in optics is Fermat's principle of least time. Time means distance divided by speed. Okay. So it turns out that different colors have different wavelengths, and speed in speed of electromagnetic wave is lambda times frequency. And since different colors have different wavelengths, they travel at different speed in a material. So in a material, V is equal to C divided by N is equal to lambda, the wavelength, divided by N. times frequency. So because lambda is different, the refractive index of a material is the same, then the speed of different colors in materials are different. And because of that, when you want to minimize times, when you want to choose the path, or when light chooses the path with the least resistance, it gets affected by the speed. Okay. So there is this simulation. The first person that get credits in with dispersion. So the name of this phenomenon is dispersion. So before the prism, here in this region, light travels all colors travel at the same speed. And then once it enters a material, they travel at different speeds, and light always follows path with the least, that takes the least amount of time. So different color choose different path. And then when there is a a change of refractive index, they again, like different colors again, choose different path. And this is why we get, we separate, or Newton separate different colors of white lights. Okay. So Newton is a smart man. Because of this, he developed telescope that doesn't use lenses. It only relies on reflection, because reflection, in reflection, there is no change of refractive index. And that's how Newton solved that problem. Okay. So refractive index depends on color, depends on temperature, and of course depends on other things. Any question? And next, we will briefly talk about rainbow. Okay, so let me check your understanding. Great. So A is reflection. I'm gonna ask a clicker question. Okay. So in the next few minutes, you need to know these options. All right, so rainbows, all of you have seen rainbows, right? And sometimes you see double rainbows. How many of you are familiar with double rainbows? Good. I didn't know until I was your age, which is I think 5 years ago. All right, so iClicker. So in the formation of rainbow, it only happen after rain typically, because you need different materials to perform dispersion and also to bend light. So here, light comes from above the droplets, and then your eyes is far below the water droplets, and the water droplets is this blue circle here. So when light enters the water droplet, it bends. The first question is, and let only spend 20 seconds on this, what is within this following optical phenomena, which one is this process? Light bends from air to water droplets. Is it A, reflection, B, refraction, C, total internal reflection? Good. 10 more seconds. 5, 3, 2, 1. You guys are amazing. Last year, every iClicker took 2 minutes. I'm not joking. So the answer is refraction. So when light enters different medium, it gets refracted, like light gets bent. So they get bent. And also, actually, it could be another answer, which is dispersion. But so it could be a nice problem for the final exam and exam 4. And then the light travels, different color travels, choose different path because they have different speeds. And then at this point, the light gets reflected. So there is this normal line here, the light gets reflected. So out of this, ignore the, out of this 3, which ray, which geometric optical phenomena is the one that I'm highlighting right now. So let's spend 30 seconds. So this region here. All right, 5 seconds. 3, 2, 1. Okay, so let's see. All right, so A is almost correct. But in reflection, there is no, there is only one refractive index. Well, A is actually correct, but C is far more correct than A. So I'll take A and C. But the answer that I'm looking for is C, okay? Because, you know, in order to fully convince you that the answer is C, you need to know the critical angle between water droplet, and air. But on the exam, the answer is C, not A. And I may throw dispersion and other things. All right, so that's good. So enough with iClicker, I think. And then, okay, so we have total interreflection here. Let me highlight here. And then light travels along straight path, and then there is refraction. Because there is, again, change of refractive index. And if your eyes is here, you will see red. If your eyes are here, you will see what is that, cyan, I think. So different colors actually arrive, like they hit, different colors of rainbow hit different water droplets before reaching your eye. Okay. So that's one, yeah. 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 Yeah, it disperses, yeah. And then, yeah, okay, any other question? And then for double rainbow, the light bounce multiple times, meaning it comes at different angle, and also light gets or exhibit total interreflection twice, and then your eyes see it as a different rainbow. Because it bounced twice, do you expect the color to be the same or get reflected? Or in reverse order? Reverse, okay, good. But all of you have seen double rainbows, right? I think you see that often. Good. Sorry, wrong camera. Okay. I think next we will do mirrors. So I have mirror here for a demo. One of the criticism for this class is that you guys say the class need class. That's why I bring mirror, so I can comb my hair before the class. Finally, we have class. Okay, so mirror, you all have seen it, and it's actually quite amazing. And let's see if I can finish the whole lecture notes. So what is a mirror? What is the material that that people use to make mirrors? Silver, that's good. In general, metal, but silver is a good choice. Okay, so silver is the one that causes reflection, metallic surface. We need, but you see glass in many mirrors. Why do we need glass? So it becomes it's to rigidify, to make it flat, because you don't want to put a big thick of silver in every mirror. They will be too expensive. Okay, and based on Fermat's principle of least time, basically says that if we have 2 points, A and B, and let's say for a mirror, the goal or the rule is that you have to touch mirror once. Turns out that the path that takes the least amount of time is the one that has the same angle, meaning the angle of incidence is equal to the angle of reflection. And in your textbook, I don't remember exactly, some books use Thera 1, Thera 2, but as long as you understand it, then different symbols shouldn't confuse you. So I have this iClicker question again. It's really simple. A laser beam strikes, so here, let me make it even easier for you so we can go fast. So a laser beam strikes a plane mirrors reflecting surface with an angle of incidence of 43 degrees. What is the angle between the incident and the reflected ray, which is this angle here? Okay. So let's spend 30 seconds. We can spend a longer time if we need it. Good. I think almost all of you already lock your answer. All right, 5 more seconds. 3, 2, 1. Good. So the answer, so what the question is asking, the angle between incident ray and the reflected ray, which is alpha here. And alpha is not a consensus symbol. I just came up with that symbol, equal to this. Incident time reflection plus reflection is 43 degrees plus 43 degrees is equal to 86 degrees. See, even I can do this arithmetic. So the answer is B. Any other question? So next is about the image formation. And I need to, there is a, so again, for optics, all this web simulation, they are even more helpful because you can see it real time instead of using ruler and draw it on paper. So this is animation of, I need to turn off the time and this, of a plane mirror. So basically, in plane mirror, if you place an object, so first object is in front of the mirror. So here some textbook use this, is to shade the area, the reflecting area, reflecting side of the mirror. And your any object actually can reflect light along so many directions, basically 360 degrees. Show 2 points. So that's the incident rays, just 2 per points. But the reality is there is infinite number of rays, and you can change the position. And basically, if you choose any position, it will hit the mirror at a different point. And then you can draw the normal, which is the vector or the line that is perpendicular from the mirror. And the reflected ray is exactly is the ray that has the same angle as the angle of incidence. Okay. Now the question, where is the image? Where is the image? When you use mirror, you can see image. Where is the image? When you look at this, where is the image? In front of the mirror or behind the mirror? Behind the mirror, right? So the image is here. We know it's here. In studying mirror, we call that virtual image. When the image is behind the mirror, then it's a virtual image. I think your book has this symbol. This is the image distance S prime. For plane mirror, S prime is negative. Okay. And in different textbooks, they call it V, and then there is, I don't know, S image or something. But in your textbooks, the symbol is S prime. So we know that the image is behind the mirror. Okay. It turns out that, again, our eyes does all the computation, and not our eyes, our brain. I think Haitham says that we see in our brains, not in our eyes. So our brain make extrapolation of the reflected beams, and when multiple rays, when I say multiple, is more than one. It doesn't have to be infinite. It doesn't have to be 3, 4, 5. 2 is enough. Then that's where the image is. So the image is behind, okay, behind the mirror. Is that clear? The image is behind the mirror. The image is virtual, meaning the image distance is less than 0. If you do geometry, then let me switch to my iPad. If we do geometry, then the height of the image is the same as the height of the object, and the distance of the object is equal to the absolute value of the distance of the image, but this one is negative because it's behind the mirror. What is the name of this type of image? Do you guys still remember from your proposal? People in that side. Aditya. No, you. Yeah. Yeah, virtual image. What does it mean by virtual image? Huh? It's not worth it? What do you mean by? It's not really there. How do you know that it's not really there? But your eyes can see it. Yeah. That's good. It's not there. One way to, one consequence is that you can see it. Wow. Sorry. But you cannot capture it. If you cannot put screen behind it and get an image, right? Like this, right? I don't see my face here. But there are other mirrors, convex mirrors, concave mirrors, where if you see the image using your eyes and then you can put camera, you can actually capture the image. That's one of the principles of reflecting telescope that Newton designed that I mentioned earlier. Okay. Anything else? So what is the magnification? So magnification is defined as, because of geometry, y prime divided by y. What is the magnification here? It's 1. Okay. So there is no magnification in plane mirror. And then magnification is also defined as minus s prime divided by s. What is the magnification of a plane mirror? S prime is equal, the absolute value of S prime is equal to S. S is the image distance. Then this one is also equal to 1. So you can, like anything else in math and physics, you can use 3 different ways to arrive to the same answer, which is very satisfying. And then you can read some of my slides by yourself. So for example, the reason why this room is not pitch black and just a little bit light here and there, because many surfaces reflect light. And it's actually much better than that. Many of the surfaces is not completely flat. So the nice thing with that is, so if this is, maybe you think that this whiteboard is very flat, but if you zoom, it's actually a little bit wavy. And every coordinate has slightly different normal lines. So normal line, as long as they are perpendicular, then they satisfy normal lines. So when light hits this part of the mirror or whiteboard, it gets bounced this direction. When it hits this part of whiteboard, it gets bounced towards different direction. And that's the reason why the room is fairly bright. We still have a lot of iClicker points. So, and you can do this yourself, I think. Let's do something more fun. There are many premats here. Okay, so I have an iClicker question for you. It relates to lateral inversion, and all of you have seen this. So the question is, you may have seen ambulances on the street with the letters of the word ambulance written on the front of them in such a way as to appear correctly when viewed in your car's rear view mirror. There is no figure, I apologize. How do the letters appear when you look directly at the ambulance? Okay, so I clicker, and let's spend 30 seconds. All right, so I think almost all of you have answered. So the answer is B. So for mirror, the name of the image that I mentioned is this type of image. We call this virtual, and there is another term for this. Not another term for virtual. We call this upright. Okay, but be careful when you read, because upright is along one axis, but actually along lateral axis or x-axis. So let's say it's z-axis, along x-axis, it gets flipped. So maybe a little bit drawing is helpful. So let's say if you want the driver to read ASU, then the objects needs to look like this, right? How to do this? Something. And then this is again not a perfect drawing because our world is 3D. This is the reason why you have to flip the letter. Okay, but along z-axis or along y-axis, the letter actually doesn't flip. This is just to show you that the order change. Okay, hope that helps. Stop here. Just create this. So it looks like that if you haven't seen ambulance before. So this is a common problem, and I'm pretty sure it will appear on MCAT. There is a plane mirror. It's a classic problem. What is the minimum dimension? So there is a person and a mirror. This happened to be a male. It doesn't have to be a male. What is the minimum dimensions of the mirror for a person in a penguin costume of height h to be able to see both their shoes and their hair? Okay. So, and then I need to switch to essay, short answer. Okay. So, so the height of the person is h. Maybe this one would. All right. 80% of you have answered. 10 more seconds. 5, 3, 2, 1. Okay, good. So this is the answer. Sorry. So the answer is the half of the person. So I couldn't find a font that looks like a person, so I chose the symbol of Linux. So basically, the mirror, the question is, if you want to save money, if you are on a budget, and maybe budget means even if you're rich, let's say you want to open, I don't know, 1 million restaurant. If you can save a little bit times 1 million times number of mirror per restaurant, you will save a lot of money, right? So this is why this class is so useful. So the answer is h divided by 2 because the eyes, if you want to see the top of your head, the light can come from the top of your head to your eyes, and then this angle should be the same. And then we know that the top part of the top coordinate of the mirror. And then if you want to see the paw, then the light bounces the paw, and then hits your eyes, and we know the bottom coordinates of the mirror. And then based on this trigonometry or geometry, the height is h divided by 2. Okay. And I have one last iClicker question. So I may take 1 or 2 minutes more. Okay, apologize for that. So next question is, how far does a person of height h, same height, have to stand in front of a mirror of height h divided by 4 to be able to see both their shoes and their hair? Okay. How far should this person move so that the mirror, so we can use even smaller mirror? And it's a trick question. All right. It's 10:59. Just put your answer, and then we can finish this discussion. So basically, so the answer is it's impossible. So it turns out that when you bring this penguin closer and further, what you do, you only change the angle, but the position is, but the minimum length of the mirror is the same. So for example, here, give me 1 more minute. If the mirror height is less, you cannot see your shoes, right? Any questions? If not, I'll see you on Monday. Okay. Yeah. You can skip the exam.